I will explain how x64 assembly language instructions are encoded at a byte level for direct execution by the CPU, with enough detail to implement an assembler. I will explain the x64 function calling convention so that you can call or be called by Microsoft API functions. I will describe virtual memory and the contents of the virtual address space of a process. I'll present pure C# code, which parses the almost ML64 compatible ASM listing files generated by Visual C++, and loads any referenced DLLs, and generates native x64 CPU bytecode, and executes the CPU bytecode in its own thread. This process is very similar to what the just-in-time compiler does in .NET. In the tutorial, I will also show how an exe file can be generated. I will now show the pure C# demonstration program so that you can see the dynamic generation and execution of x64 CPU bytecode in action. Double-click the icon for the file C# execute memory to start the program. Two windows appear, a GUI window and a console window. When the Go button is pressed, the assembly language source code in the left panel is assembled and executed in a new thread. If the assembly language code calls functions that print text to the console, like printf in the C runtime library, then the console will show that text. We can modify the string constant in this example and then press the Go button again. When the program is assembled and executed, different text is printed to the console. The right panel shows how the C# program parsed the assembly language source code in the left panel. This partly serves as a sanity check of the parsing. You can see the addresses selected by the assembler for functions and labels. And you can see the bytecode generated for each assembly language instruction. This bytecode is generally the same as the bytecode generated by Microsoft's ML64 assembler. The generated bytes for the code and data sections are also shown. Notice the string constant in the data section. Click on the Example 2 button to fill the left panel with an assembly language program which does floating point math among other things. Press the Go button to assemble and execute that code. This assembly language example program uses Windows API functions to get information about DLLs loaded into the address space of the process. Because the thread executing this assembly language code is within the same process as the C# program, you can see the DLLs related to the .NET Common Language Runtime (CLR) in this list. This program also determines which DLL has an address range that includes the powf function, and also prints out the bytecode stored there. Then, various examples of integer and floating point arithmetic are shown. Thus, you can see how these things are done in assembly language. Now click on the Example 3 OpenGL button to fill the left panel with assembly language code that implements a simple OpenGL program and press the Go button. The window that appears is drawing a textured rectangle and a few lines. The texture is 2048 by 1024 pixels and is being completely updated every frame by a formula. A CPU-based video decoder might update an OpenGL texture this way to present the video in an OpenGL environment. Because this is executing in its own thread, we are free to assemble and execute code in other new threads. We can start multiple instances of this OpenGL animation. All of this texture updating is very punishing on memory bandwidth and PCI bus bandwidth, though. Although closing the main window of the program terminates all of the threads we created, a change in a single line of code can make these created threads persist. Let's start the C# program again, and let's open a simple C++ project with Visual C++ 2010 Express. This C++ code simply prints "Hello World" to the console. First, be sure to configure the program to compile for 64-bit mode execution. It's tricky to do this with the Express version of the Visual C++ 2010. I'll provide instructions in the tutorial, or you can just search for instructions for compiling for 64-bit mode online. You can make the compiler generate assembly language output with a compiler setting. Here I compile and execute the program, which has the effect of generating an assembly language file. Now I can simply drag this assembly language file, file extension .asm, into the left panel of the C# program, and then press the Go button to compile and execute it. Note that if I then modify the print statement and recompile and drag the updated ASM to the C# program and press the Go button, new text is printed to the console. One severe problem with my C# program is that it will crash if the generated bytecode crashes. Obviously not good for playing with assembly language. I know how to fix this, and I will try to fix this before the tutorial is published.